Have you ever just, looked around and wondered, what is all this stuff really? The chair you're on, the air you're breathing, even the device you're watching this on. On the surface, it all seems so different, so solid. But what if I told you that beneath all that, there's a hidden world, a world that's constantly moving, buzzing with energy, and interacting in ways we can't even see? So, that's the big question we're tackling. What is everything really made of? The answer is, well, it's both incredibly simple and at the same time, totally mind-blowing. And I promise, once you get it, you'll start to see the world around you in a whole new way.
All right, so here's our game plan. We're going to start with the basics. What is matter? Then we'll zoom way in to see what it's actually made of. We'll look at the rules these tiny bits follow, how that gives us solids, liquids, and gases, and how they can change from one to another. And finally, we'll connect it all back to everyday stuff like why swimming actually cools you down. Let's do this.
Okay, first things first. Scientists needed a single word for all the stuff in the universe. Everything. And that word is matter. But what does it actually mean scientifically?
It's a really simple, elegant definition with just two key parts. For something to count as matter, number one, it has to have mass. Think of mass as just how much stuff is in an object. And number two, it has to occupy space, which just means it has volume. If it checks those two boxes, congratulations, it's matter.
So just think about that for a second. The air all around you? Yep, it has a tiny bit of mass and it definitely takes up space, so it's matter. The water in your glass? Of course, even a single tiny grain of sand. A star, a cloud, the food you eat, it is all matter. It's the fundamental building block of literally everything you can touch and feel.
Now, for a really long time, people argued about this. Is matter continuous? Kind of like a smooth, unbroken block of wood. Or is it made up of tiny little bits, more like a beach made of sand? The answer to this question, well, it changes everything.
And the big reveal is, matter is not one solid thing. It's actually made of countless incredibly tiny particles. But hold on, if we can't see them, how can we possibly know they're there? Well, believe it or not, a super simple experiment proves it beyond a doubt.
You've done this a million times. You take some salt, you stir it into water, and it disappears, right? But here's the crazy part. The water level doesn't go up. So where did the salt go? It didn't just vanish. The tiny salt particles actually slipped into the invisible gaps between the water particles. This one simple observation is the ultimate proof that matter isn't solid at all. It's full of tiny empty spaces.
Okay, so we've established matter is made of tiny particles with spaces in between. But how tiny are we talking? Like, are they the size of dust specks, or are they something else entirely?
Get this, just 2 or 3 tiny crystals of a chemical called potassium permanganate have enough particles in them to color 1,000 liters of water. That's like 5 or 6 bathtubs full of water. For that to happen, each one of those tiny crystals has to break apart into millions, probably billions of individual particles. They are so small, it is genuinely hard for our brains to even comprehend.
So now we know that everything is made of these impossibly small particles. But what are they doing? How do they behave? Well, it turns out they follow 3 simple, golden rules that basically explain, well, almost everything in our physical world.
Here they are, the 3 golden rules. First, as we saw with the salt water, particles have spaces between them. Second, they are never ever still. They're in constant random motion, jiggling, vibrating, and zipping around all the time. And third, they attract each other. There's a force pulling them together. And really, the entire story of matter is a battle between that constant motion pulling them apart and this attraction pulling them together.
Now, that constant motion leads to something we've all experienced called diffusion. It's the reason you can smell hot food from across the room. The aroma particles from the food are just randomly moving, spreading out, and mixing with the air particles until they bump right into your nose. And since heat is just energy, it makes the particles move faster, which is why you can smell hot food way better than cold food. Diffusion happens way faster.
So if you take those 3 rules we just learned, spaces, motion, and attraction, they directly lead to the 3 states of matter we all know and love: solid, liquid, and gas. The only difference between a block of ice, a glass of water, and steam is just how those 3 rules are playing out.
Let's break it down really quick. In a solid, that attraction force is super strong. It wins. The particles are locked in place, giving it a definite shape and volume. In a liquid, the particles have a bit more energy. They can slide past each other, so they take the shape of their container.
And in a gas, well, the particles are moving so fast that the attraction force barely matters. They just fly all over the place, filling whatever space they're in, and you can easily squish them together.
And this picture says it all. You can see it right here. In solids, the particles are in this tight, neat formation. In liquids, they're still packed in, but they're all jumbled up, free to move around. And in gases, it's just total chaos. They're super far apart, zipping around randomly. It's the same exact particles, just with different levels of energy and freedom.
So, since the only real difference between these states is energy, it makes sense that if we add or remove energy, usually is heat, we can force matter to change from one state to another. And we see this every single day when ice melts into water or water boils into steam.
Imagine we take some ice and we start to heat it, right? We're pumping energy into those water particles, making them vibrate faster and faster. But right as that ice starts to melt into water, something really weird happens if you're watching the thermometer.
So you're adding heat, but the temperature gets stuck at 0 degrees Celsius. The ice is melting, but it's not getting any warmer. The same thing happens when water boils. The temperature hits 100 degrees and just stays there, no matter how much you crank up the heat. So if the energy isn't making it hotter, where in the world is it going? The answer is this absolutely amazing idea called latent heat. The word latent just means hidden. So this is hidden energy. It's not being used to raise the temperature. Instead, that energy is being used for a specific job, to break the forces of attraction holding those particles together. It's the energy needed to literally pry the particles loose from their solid structure into a liquid, or from a liquid into a gas.
And sometimes, matter just decides to take a shortcut. It's a process called sublimation, and it's when a solid jumps directly to a gas, completely skipping the whole liquid phase. The classic example is dry ice. It doesn't melt into a puddle, it just sort of vanishes right into a gas.
Okay, let's bring all this amazing science back down to Earth. This whole process of changing states, especially from a liquid to a gas, is behind one of the most common things we feel every day, the sensation of cooling. So think about it. Why does sweating cool you down? Well, as that sweat evaporates, it has to turn from a liquid to a gas. And to do that, it needs energy, that latent, hidden heat we were just talking about. And where does it get that energy? It steals it from your skin, leaving you feeling cooler. It's the exact same reason that nail polish remover feels freezing on your hand. It evaporates super fast, pulling a ton of heat away with it. And that water on the outside of a cold glass? That's just the reverse. Water vapor in the air hits the cold surface, loses its energy, and condenses back into a liquid.
So let's go back to where we started, a simple glass of water. After all this, it's not just a boring clear liquid anymore, is it? It's a chaotic universe of trillions upon trillions of particles, constantly moving, jiggling, sliding past one another, all held together by invisible forces. It's a substance just waiting for a little bit of hidden energy to break free and fly off into the air. When you understand the unseen world of particles, even the simplest things become absolutely extraordinary.